zu unserer Ringvorlesung Eye-Tracking 4.0. Wie Sie sehen, unser Vortrag wird aufgenommen. Sie sollten zustimmen, dass Sie bereit sind, dass das aufgenommen wird. Heute haben wir einen Gast aus Schweden bei uns, Professor Kenneth Holmqvist. Kenneth spricht und versteht Deutsch ganz gut, aber er wird ganz gerne seinen Vortrag auf Englisch halten. Deshalb switche ich jetzt gerade auf Englisch und erzähle weiter über Kenneths Curriculum Vitae. Kenneth Holmqvist hat an der Universität, you studied at the University of Lund in Sweden, correct? 1988, you got your master's degree in computer science. And then you went on to do a PhD in Lund, where you stayed. Apparently you liked that part of Sweden very much. First as a researcher and then as a professor in the Department of the Faculty of Humanities, correct, Kenneth?
In cognitive science.
Cognitive Science, Department of Humanities, where you built one of the most famous laboratories in the world for eye tracking, right? That attracted at least 1,000 people to Lund over the years, correct? I mean, you had the summer school, very famous summer school on methods in eye tracking at the University of Lund. And then in 2017, Kenneth decided he'd like to change, and he came first as a visiting professor here at the University of Regensburg, and later a number of leading laboratories. And since 2018, he's research professor at the Department of Psychology at the Nicholas Copernicus University in Torun, Poland, where he is actively pursuing his research with colleagues there in psychology. Kenneth and I met, I was just thinking, Kenneth, I think we met first in Freiburg, at Christoph Klein's summer school in eye tracking, correct? Yeah, that was, I think, the first time we actually met. And yeah, since then we've interacted here in Regensburg and have applied for a number of interesting projects with EU funding. And Kenneth has a very interesting collaboration with a company in Israel that develops eye tracking equipped virtual reality systems and augmented cognition systems, augmented reality systems that are the future of this type of research. Today, Kenneth is going to tell us about a very interesting topic, looking at nothing, the role of visual imagery in guiding voluntary eye movements. Okay, Kenneth, the floor is yours, and we're very interested in your topic. Thank you.
Thank you very much, Mark. So I'll try to share my screen. Work. Right. Yeah, I'm going to talk about looking at nothing. And it differs, of course, from most other research, which is about looking at something, looking at text or looking at images or looking at the real world. But in this line of research, we have people look at nothing. And there is a particular reason for doing that. Here's the outline of my talk. I thought I'd first give you an example of what looking at nothing data look like. I think it helps understanding. Then I'll try to show that the modality of the encoding doesn't matter. And with this, I mean where the information comes from has no direct influence over the looking at nothing eye movements. I'll spend some time talking about visual indices and why we need to record eye movements in complete darkness. That's necessary to counter one of the criticism against this line of research. And then another very important question, namely, is it functional to look at nothing? Does it help us? Then I'll talk a little bit about the theories behind looking at nothing. The problem of shrinkage, which I'll tell you about, and the solution to that. And then finally, I'll talk about applications of the paradigm of looking at nothing. Right, here's my example. It was one of the first studies we made. This is a person who is looking at the white screen. You see the video recording from this participant on the right-hand side here. There's a little gaze marker and there's a white board. And there will be a voice describing the scene to the left. So the participant has never seen this scene. It doesn't exist, the scene. It's just entirely made up. So, and then we recorded eye movements while the participant was listening to this. Now, it's very important in this kind of study to make sure that the participant doesn't understand what we are up to. So we are telling them that they are in a memory experiment where they ask them to memorize things. And the reason that we have put something on their head is that we are measuring their pupil dilation as a measure of the cognitive workload, the effort of memorizing this.
Imagine a two-dimensional picture.
Now it's working.
Okay.
At the center of the picture, a large green spruce grows. In the top of the spruce, a bird is sitting. To the left of the spruce and to the far left in the picture, there is a yellow house with a black tin roof and white corners. The house has a chimney on which a bird sits. To the right of the large spruce and to the far right in the picture, a tree grows, which is as high as the spruce. The leaves of the tree are colored in yellow and red. A bit above the tree, at the top of the picture, a bird flies. Between the spruce and the tree, there stands a man in a blue overall who is raking leaves. In front of the spruce, the house, the tree, and the man that is below them in the picture, there is a long red fence which runs from the picture's left edge to the picture's right edge. At the left edge of the picture, a bike is leaning towards the fence, and just to the right of the bike there's a yellow mailbox. On top of the mailbox, a cat is sleeping. In front of the fence, that is below the fence in the picture, there's a road which goes from the picture's left edge to the picture's right edge. On the road, to the right of the mailbox and the bike, a black-haired girl is bouncing a ball. To the right of the girl, a boy who wears a red cap is sitting and watching her. To the far right on the road walks a lady who is wearing a big red hat and who has books under her arm. To the left of her, on the road, a bird is eating a worm.
Then I'll stop sharing this and then I share my PowerPoint again. Right. So I hope that you could see what was going on there. This participant looked at the white board as if the figure was there, although it wasn't. It was just white. Now, a typical mental imagery or looking at nothing experiment is often built like this. There's one encoding phase, It could be a visual encoding. They could see a picture like this. And then there's a recall phase where they are asked to retell what they had looked at. So in a sense, it's a memory experiment, an experiment of episodic memory. We could also do what we just looked at. We could have a verbal encoding. So they will listen to a spoken scene description, which you just heard here, the encoding, and then they would, in words, recall what they had looked at or learned, memorized. And then what we do then is we compare the eye movements during the encoding phase to the eye movements in the recall phase. And with our hypothesis, if there is imagery or some form of imagery here, then the eye movements would be similar. And yeah, this is what it looks like. Here's one participant. This is verbal encoding. They heard exactly the scene description that you also heard. And this is the eye movements that were made during the scene description. And these are the eye movements when the participant, him or herself, retells the same scene. And I think you agree that they look similar. The quantification of that similarity is not trivial, but there are methods to do it. I'm not going to go into it. It's a bit mathematical, so I'll leave that. But there are ways to quantify the similarity also. And we did this, and with our 24 participants, we found that what we measured here is the number of mentioned objects to which there was a corresponding eye movement. So they are saying the house. Is there then an eye movement to the place where the house should have been? And we count those instances. And we have one strict criterion and one little looser criterion. And in both cases, there's a strong effect. They make eye movements to objects that are not there on the white screen. And also, there's no difference between visual encoding of a picture and verbal encoding from a scene description. You might have thought that there would be a difference because, well, a visual picture is something quite different from a verbal description, after all. One is, and there are theories saying that vision is very different from verbal information. But at least when it comes to looking at nothing eye movements, there is no difference when people are recalling that content. They make exactly the same eye movements in exactly the same amount. Now, years later, we made this study because we were thinking, okay, spoken language and visual pictures, that's one way to encode, but we also encode and memorize from text. When we learn things, we often read. So we were thinking it would be interesting to do this with text encoding. So we built two experimental conditions. The scene looked like you can see here, it's a scene on the beach. There's some water here. There are houses and other things. There's a sun and a mountain in the background. And we made one text with 3 paragraphs that correspond to these 3 parts of the scene. So in this case, the top paragraph describes the top part of the scene. The middle paragraph describes the middle, and the bottom paragraph describes the bottom part of the scene. And the reason that we are manipulating this is that people have, and I think you all have experienced this, when you are reading the newspaper, for instance, and you remember something that was written in the newspaper, you can often say, yeah, it was on this left-hand side of the newspaper up in the top left corner. We have that sort of text memory. And reading researchers have also spoken about the text memory that we have when we read, that we can make regressions far back into the text. So it is possible that people remember in memory the text more than the picture. To test whether this is the case, we made an incongruent condition in which the top level of the text describes the bottom of the scene, and the bottom of the text, bottom paragraph, describes the top part of the scene. So they would read this, and afterwards we gave them a blank monitor, white, and then we asked them to retell it. And then it could be the case that when they were saying sun in this incongruent, this is the incongruent is the interesting condition. If they were saying sun, then they could look at the top part as the picture that they have never seen, but they read about it, the sun here. So they will look at the top. But if they remember the text, if the text memory decides they're looking at nothing, then they would look here at the bottom, because the sun was described at the bottom. Now, that's basically the experimental design. So we measured, do they look at the object, when they speak about objects, do they look at a place consistent with the image content or with the text content or the text display? And here are the relevant data. Blue here shows congruent scene description and incongruent scene description. So people looked at things that were people looked at objects that were congruent with the scene description and not so often with congruent with the text. Yeah, and there was no and this this shows that when people have read a text which describes something spatial, they're looking at nothing eye movements to a higher degree follow the content of the text, and not to any higher degree the display of the text, which we could interpret as people remembering the content rather than the shape of the text. So, so far, it seems like the modality of the encoding doesn't matter. People make the same looking at nothing eye movements, whether they have encoded into memory from a visual scene, from a verbal scene description, or from a textual scene description. It doesn't really matter which it is. All three encoding modalities result in imagery looking at nothing behavior in the eye movement recording. Now, I need to say something about the scan path theory and Norton and Stark. Norton and Stark made a study in 1971 in which they asked participants to look at the scene and then remember it, and then later they could look at it again. And they argued from a very small sample of only 2 participants that people encode the order into memory. That is, once you've looked at the picture, next time you look at it in the same order. And this has been a very influential theory. And I still today hear, when I talk about mental imagery research, I still today hear people say that, why don't you use the order of the the looking at nothing data. And I have to tell them that there's no support in any of the looking at nothing studies for Northern and Stark's theory. And it's because the locations are reinstated during looking at nothing, but the order is not. And both these publications show that this is the case. People look at the same places, but not in the same order. Yeah. When we were doing our first study, we had a problem with a psychologist by the name of Zenon Pelishin. Pelishin argues against mental imagery. He argues that it doesn't exist, that our internal representation of the outer world is propositional in its nature, that is essentially sentences. And he argued that studies of the kind that we do, of the data that I showed you recently, the reason that we get the results of this kind has nothing to do with mental imagery or spatial structures in memory. No, he said, the reason that we get these results is that there are small features in the empty monitor or the plane, and you can take spatial locations on with these features and link them to items in your working memory. So if I'm thinking tree, I can place my tree anywhere on the empty monitor when I'm memorizing it. And when we then recall it, we just do, this is where I imagine X to be located, Pelishin said. And he gave a talk in Sweden in 2005 when we were working with our study. And he said at that talk that the only way to prove that visual indexes has nothing to do with it is to record eye movements in complete darkness. Because of course, in complete darkness, you have no features to hang your propositions onto. And Pelishin said, it's impossible to record eye movements in complete darkness. So we cannot know about this. He thought it's impossible to record eye movements in complete darkness, but yeah, it is. So we set up this experiment. So encoding was done, visual encoding, of course, they had to look at the picture, but then recall was done in complete darkness. In the verbal case, they encoded from the scene description in complete darkness and they recalled in complete darkness. There are some challenges with recording in complete darkness. First of all, you need to make the room totally dark. There must be not a single source of light there that Pelishin could say that we hang prepositions on. So we covered everything. But we then quickly noticed that the infrared illumination of the eye tracker gave our participants a reference point. So we had to change the infrared illumination to light frequency outside of what human eyes can see, something like 1100 nanometers. Then we recorded the data. We used more participants because we were unsure what would happen. And a lot happens to participants in complete darkness also. They start to blink a lot and their pupils become huge and they become slightly disoriented. Now, nevertheless, despite all these troubles, we still got good results. So with picture description, listening to scene description and retelling the scene description, we still got a really great results, very much above chance. And Pelishin was wrong. Yeah. So what does this tell us about mental imagery in episodic memory? And yeah, there are some things I think we can say. First of all, content representation is probably not propositional, and our completeness darkness study points to that. The results are probably not caused by motor memory, which Norton and Stark thought in the scan path theory, that it's somewhere a motor memory of the eye movements that is stored. I don't think that is the case. At least when activated as eye movements, the memory content representation probably includes spatial properties such as extent and range, direction, and spatial relationships. This conclusion I think we can draw from eye movement research, looking at nothing research. And all these findings support theories of mental imagery by Koslin and others. Now, people have talked about this for quite some time. In fact, already in the 60s, Neisser argued that eye movements are actively associated with the construction of visual images. And Hebb claimed that eye movements are necessary to assemble and organize part images into whole visualized image. It's consistent with what we find, but the organization of part images into whole, it's consistent with our data, but it has not been specifically investigated. Looking at eye movements and the imagery that we think is involved in it could also be a reenactment or simulation of neural activity, that when we are recalling a scene, we are driving the eye movement as if the scene were in front of us. And there are theories saying that this could be the case. Interestingly, location memory and object memory are related to two relatively independent systems of the visual system of the brain, the dorsal where pathway and the ventral what pathway. And the eye movements that we're measuring, the looking at nothing eye movements, they are clearly where. They are pointing at the where of some memory content. And the memory content is related to the what pathway. It could be that this is part of the organization of the memory. I don't know. But MRI studies have shown that there is extensive overlaps in neural processing when an event is internally simulated, like mental imagery, and when the same event is actually perceived. And there are some studies by Koslin on this. Another question that the looking at nothing people have wondered about is this an epiphenomenon or is it functional? Or in other words, does it help us to look at nothing? Is it good for us? Or is it just something that we do as a side effect of memory retrieval? It could be. I mean, people have claimed that this could function as cues to activate memory. Altman and Richard and Spivey said so. It may also be the case that it's part of arranging relevant parts of a visual scene into a whole. And several people have claimed that this to be the case. And it could also be the case that fixations to nothing can act as facilitatory cues during memory retrieval. Several people have pointed this possibility out. So 10 years ago, we didn't know. We didn't know whether it's just an epiphenomenon or if it's functional. But there have been studies since, and some of them are ours, so I'm going to talk about them. The first thing that we did, and also others did, was in the recall phase, when people are recalling from memory, they spontaneously look around. So what we did was we gave them not just a white monitor to look around it, but a fixation cross in the middle. And then we told them to look at that fixation cross when they are recalling from memory. We're forbidding them to make looking at nothing eye movements. And then we wanted to see, does it impair recall? And it does. So we looked at the language that they produced. And we categorized the language. There's a theory in language that you can categorize what is being produced as either substantive or summarizing. Substantive means that people talk about specific items. And summarizing, of course, they summarize the whole scene. And the darker bar here shows free viewing. They are allowed to make looking at nothing eye movements. Lots of mentioning of concrete objects. When we force them to look at the central fixation cross, there are much fewer. But summaries of the whole scene, there are not that many when they are free viewing, when they can be looking at nothing eye movement. But when we force them to look at the central fixation cross, there are many more summaries of the general scene. We also counted the total number of objects and locations that they mentioned, and there were fewer of them when they were forced to look at the central cross. This suggests that it's functional. And then there was a follow-up study, and it's more complicated to understand, but I'll try to tell you. You can teach people an association between objects and places on an empty screen, and then manipulate their gaze towards positions where either the object was or it wasn't. Now, where it was is called congruent condition. I'm only interested in the bottom plots here, plots B. The congruent condition is where when the eye movement was made to a place, that place was congruent with what they are asked to recall. And if it's incongruent, it's red. So this shows that the response accuracy, how correct their recall is better if they are asked to look at the position on a screen where the object that they are asked to remember has been. Yeah, and this is not the only thing, but also the reaction time in recalling the object is lower when the object, when the eye movement is congruent with the position of the object. And this result has been replicated several times. So I think the summary of these studies is that looking at nothing facilitates episodic memory retrieval. It's good for us. It's good to look at nothing. It's easier to remember things. Accuracy improves, the quality of the memory improves, and speed improves. It's a good thing. So here are some other findings of general looking at nothing. Longevity. Most looking at nothing studies, they don't last very long. You encode and then 5 minutes later you recall. But Mattarelli and Mast, they waited a week and found that people still made looking at nothing eye movements to the items, to the locations where items were originally encoded. So it seems that whatever this is in memory that drives these eye movements, it lasts at least for a week. Now, another curious finding that has been reported several times, but no one has really made an in-depth study of, is the fact that fixations during recall are longer than during encoding. And this plot here is from Wang et al. It shows over 5 seconds, from the onset of the picture in the picture in the encoding phase, or the onset of the white monitor for recall. And it's not a small difference. They are twice as long, the recall fixations. Usually fixations are longer when the item to be processed is somehow effortful. For instance, in reading, when people read text and they look at an uncommon word, the fixation duration is almost always longer. The same thing if you look at a scene and there's some unusual object that is not expected in the scene, then the fixation duration is also longer. So it could be that recall, as looking at nothing recall, is more effortful than scene coding. This was the interpretation by Balai. And I think it's reasonable, but I think there also are many details that can be explored here as to understand why fixation durations are so much longer. Right. Another thing that has troubled the looking at nothing researchers is shrinkage. So I'll illustrate shrinkage here. This first participant is looking at nothing eye movements that cover a large space, the whole white board or monitor, completely. This participant 2 makes smaller eye movements, but they are still looking at nothing eye movements. And then participant 3, the tiniest little eye movements you can imagine. And we didn't know what this was. It messed up our data analysis, and we didn't know what to do with it. But Finke, 1989, writing about mental imagery from a completely different perspective, he said that subjects change the size, change shape, and reorganize mental imageries, which would then lead to idiosyncratic eye movement patterns. Yeah, so if we take a lot of participants during encoding and we put a little bounding box around their eye movements, then it gives this plot here to the left. And if we do the same thing for the recall eye movement, it looks like this. So there's a general shrinkage behavior. Yeah, recall scan plots cover smaller areas. Now, we still don't really know what's going on during shrinkage, but we know one thing. In a study from 2011, we asked our participants to fill out a questionnaire about their spatial imagery ability. And then we correlated it against the extent of their looking at nothing eye movements. And we had thought that people who are good at spatial imagery, they would make use of a larger space without looking at nothing eye movements. But it was the very opposite. People who are poor at spatial imagery, they make larger eye movements. And people who are better at spatial imagery, they make smaller eye movements. Now, this was really strange for us. But if you think that, if you remember that looking at nothing eye movements are functional, then it makes good sense. Because if you're really good at remembering things and thinking spatially, then you're in less need to make eye movements. But if it's effortful and difficult for you to remember because it's hard, then it makes sense that you make larger eye movements. I think I should say in this context also that it has been shown that the extent of eye movements to blank spaces diminishes with practice. The more you learn about a scene, the smaller the extent will be. So this is something that we employ when it's difficult. It's functional and it's good to employ it when it's difficult. Now, we have recently published a paper where we deal with the problem of data analysis that follows shrinkage. So we made an algorithm that corrects for shrinkage. It simply takes the recall eye movements and stretches it like this. And this must be done with care, of course. I will not go into detail how this algorithm works, but essentially it has, if we imagine here is the yellow is the encoding scan path and the green is the recall scan path. It produces a corrected recall, the pink, and it does that in a number of iterations. So it takes the green and moves it to where the pink is. And it's quite efficient and quite good. We validated it, and you need to see the paper to see our validation, but it seems to work. Here are example output for 3 images. So people first looked at each of these images here. And this is encoding is where they looked. I don't remember the total participants here. Maybe it was 40 or something. And here is the heat map of the gaze when they looked at each of these figures. So in the first figure, they looked a lot at number 3 here, the figure, the desk, and also the little robot here in the bottom corner. We then unshrunk the recall scan path for all of the people, and then we plotted the corrected recall. We call it matched encoding in the paper, but it's essentially corrected recall. And this allowed us to see what they prioritize in recall. So here it was the desk clearly, but they did not to any large extent look at the sign for number 3 or the calendar next to it, and they seem to have completely forgotten about the little robot in the corner. And similar things happen here with the train set. It's not that similar, not that dissimilar. And here in this figure, there's a child here with a ball, and then there's this text. And the text is much remembered, the ball also, and the child is more forgotten. It's more recalled, but the ball is more forgotten. And this not only does it allow us to make more detailed and better statistics when we have corrected for shrinkage, but it also allows us to make studies of what is prioritized during recall, which I assume is memory research. Yeah, it is memory research, and I'm not a memory researcher, so I really have no competence of speaking about this. But I find it intriguing that you can do this. Not much has been done in this field, although it seems like an obvious way to go. in our paper, there were lots of people in the photos in our paper, and we put bounding boxes around all people to measure their size in the photo. And then we looked at how much they were recalled in the corrected recall fixations. And it turned out that in recall, people only remember, our participants only remember people in the figures if they are above size 9. Every participant, every person in the figure below that size is forgotten. Yeah, you can also use this for photo retrieval as an implicit human-computer interaction. So the scenario is the following. You have a user who is looking at nothing, a white board or the wall. There's an eye tracker that measures the eye movements and machine learning. So the eye tracker measured that, oh, there's a scan path here. And the machine learning looks through a photo database with recorded eye movements and picks the photo with the most similar eye movements. So it is, if this works, then you just look, you think about the photo and you look at a monitor and the computer brings you the photo. Mind reading. We tested this in the database with 100 photos, and in 72% of the cases, the right photo is among the top 3 suggested by the algorithm. It was not, it is a little bit poorer than I thought it would be, but then again, we didn't have the shrinkage compensation when we did this. I think with shrinkage compensation, we would get much better data. There are also MRI studies on photo retrieval, where you put people in the MRI and they are asked to think about the photo, and then the photo appears. They have much smaller databases. And so I think we're slightly ahead of the MRI people in this particular competition. This has also, mental imagery has also been used in education science, because of course, a mental image could be the outcome of a learning process. So the data I show here, the participants were learning this pulley system, how it works. When you pull here, it lifts the weight more or less than you expected, depending on the nature of the pulley system. And people learned this either with text only, or they had this picture slightly before the text for 600 milliseconds, for 2 seconds, or as long as they wanted. And after they had learned, they were asked to recall what they had learned. And people who had looked at the image at least 2 seconds, they made eye movements, looking at nothing eye movement, that corresponded to the nature of the pulley. And so was the same was found in the self-paced before. It's a little bit more difficult to see, but the same as the cards we made here. While seeing it for only 600 milliseconds was not enough. So looking at nothing can also be used to study learning processes. So to summarize, looking at nothing, it's a robust paradigm with several possible practical applications. Looking at nothing facilitates memory retrieval from episodic memory. The encoding modality, scene, speech, or text, does not seem to matter. But there are many interesting research questions that remain. Priority and recall. Why do people recall some things more than others? Why are the fixation durations so much longer? What are the factors involving shrinking? And also, all of these studies have been about 2D imagery, pictures, but we have 3D imagery as well. Can eye movements be used to study 3D imagery?